1%. That is the amount of the sun's energy that the Juno space probe is able to absorb as it is orbiting the planet Jupiter. Now, if I were to put it around Earth, if it were in Earth's orbit specifically, it would be able to absorb about 23% of the sun's energy. So as you get further, the point is, as you get further and further away from the sun, things get more and more inefficient when it comes to solar technology. Also, the solar panels on the Juno space probe are massive. There's 3 of them, and each one is about the size of a parking space for a school bus, 30 feet long and 9 feet wide. Now, if I were to put it, if we were to actually calculate the power generation in watts, if I put it in Earth's orbit, and it was giving me power right now, it would have about 14,000 watts of energy, which is, I believe, yeah, it's a little bit less. I think it's about a tenth of the ISS power output, which is pretty insane. And then as soon as we put it on Jupiter, it immediately goes down to 400 watts. Now, there have been several deep space probes, like Voyager, which have managed to go past Jupiter and still work. And yet they don't have solar panels, and I wonder why. How are they able to do all of this amazing stuff? Look at this beautiful image. Look at that beautiful image of the Earth. That tiny little half-pixel image that was captured by Voyager in the early 90s. And this image was very, very important. I think it has a lot of meaning behind what it means to be a human being on a tiny little grain of sand in the middle of an infinite universe. So here's the thing. Here's the little secret to this power. It's a certain device, and it's known as a RTG, or radioisotope thermoelectric generator. It's quite a mouthful. So we're going to divide it up into 2 words. Okay, we're just going to take it radioisotope, okay, and thermoelectric generator. That's what we're going to do, okay? All right, so we're going to start with the radioisotope part first. Okay, so radioisotope, that comes from, actually, it's a piece of radioactive material. Surprise. And it is specifically the radioactive material that we use in most, and actually in all deep space probes, is plutonium, plutonium-238. And the reason why plutonium is so great is because it is able to actually last for a pretty long time and actually generate quite a bit of heat. Like, it has a half-life of like 87 years, and it constantly, like, when you first pull it out of the creation oven for plutonium, it's basically, I think the temperatures are in like thousands of degrees Celsius or Fahrenheit. It's actually, I believe it's like over 1,000 degrees Celsius, and somewhere around 5,000 degrees Fahrenheit. Insanely hot. And this is how the chain reactions take place. It's basically nuclear fission, where the individual nuclei of the atoms are so dense that as the half-life progresses, because it has such a short half-life, that's why it has such a short half-life, because everything is so dense inside of the nucleus. So it will split, and then as it splits, it creates a small amount of energy. And depending on the element, the energy can actually can vary greatly. With plutonium, it's a lot of energy, and it's mostly in the form of heat. And there's a piece of plutonium right there, just for reference. As you can see, it's glowing, and it glows all the time. When you first make it, it's like that. And it will stay that way for a very, 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 very long time. So, yeah. Now we're going to talk about the thermoelectric generator part of it. So, with thermoelectric generators, basically the basic principle is you want to think about metal first. So it's individual strips of metal. Each strip of metal, now if you took each strip of metal and you made one side hot and the other side cold, you would see, if you could look at it atomically, you would see that the electrons and the next to the hot side are moving around a lot and are trying to get to the other side. They're trying to move less. That is kind of the idea of what the electron wants to do. It's like, oh yeah, I'm just sitting here and I've got to move less. And it's the same way with several other materials, but this is something that you usually learn in chemistry class when you're looking at states of matter. And then we have to think about it this other way. So not only are there basically conductive materials that have a lot of electrons in them, an extra electron specifically, but there's also p-type materials which have one less of an electron. And so these basically have electron holes. That's what you can think of them as. And so when we see a regular thermoelectric generator, what we're looking at is, you can see basically a small, just several little junctions of metal. The pieces of metal are next to each other, the p, n, so positive, negative type, positive type, negative type, and each one has these particles inside. So when I put the two next to each other, so if I have a p type and an n type, what will happen is if I apply heat, basically the polarities are inverted. Because what happens is, okay, so a bunch of these spaces will come up and will go down, and then a bunch of these electrons will go down, and that will cause one side to be negative, the other side to be positive, and then the other side to be negative, the other side to be positive. So it's basically inverted. This inversion is basically what encourages the electrons to move around. And then you can put all of these little junctions, these little pieces of metal, together in series like a puzzle. And then you can use that to actually generate meaningful amounts of electricity. Now, this method of power generation has actually been pretty popular especially after the whole idea of using them in deep space probes, mainly in car engines or areas that have a lot of excess heat, because most of the time when we produce electricity, most of it is given off in waste heat. So what we wanted to do was, people were like, oh yeah, this is a great idea, let's just use thermoelectric modules to collect all that waste heat and convert it into usable electricity. And that's pretty cool. But I thought about looking into it more, and actually you could find more energy in areas that don't have as much work involved, like human skin. Human skin has a lot of heat energy in it. I believe you have enough to basically, I think like 60, 80 watts, I believe, for the human body in terms of heat energy. Yeah, the mitochondria are great. So yeah, your body basically produces a lot of heat. And I did an experiment in one of my replicates previously where you actually used, I used some Peltier tiles, and I attached them to my skin basically, and used them to generate a small amount of electricity. And I realized that people were actually have had this idea for a very long time. Actually, for the past like 5 to 10 years, people have been doing a lot of different experiments. Universities have been trying to develop cool technology for space, like spacesuits that are powered by the human body, and even some companies have been developing products that are powered by the human body, like Matrix Power Solutions. They've made a smartwatch, which is basically completely powered by the human skin. So you can wear it, and it's pretty damn cool. And then I went a little deeper into it. I was like, wait, so yeah, we can get heat from our bodies, and I'm like, yeah, but that doesn't really sound that fun. Like, is there any way we can just get heat, like we can get electricity passively from temperature differences in the air? And it can be done. There are several different IoT systems that people have been coming up with, really low power sensors that have like a bunch of aluminum fins on them that kind of dissipate the heat very quickly, and you can use them to generate small amounts of electricity. But recently, a few physicists in California actually discovered this new device that basically generates electricity from the night sky. So how that works is, it's basically, the concept is, if you think about it, the sun basically puts energy down on the Earth during the day, and then as soon as nightfall occurs, that energy leaves the Earth. But when you think about it, there's, of course, with every action, there's an equal and opposite reaction. So what happens is, when there's energy being put in, as soon as that energy leaves, there should be energy involved in that energy leaving, right? It takes energy in order to get that energy to move. So the night sky is basically, the power of the night sky is basically causing all of this energy to move. So what they did was, they basically created this device that kind of goes into that and hacks it, and basically creates a reverse solar cell, kind of. It's really cool. So this is a diagram of it, and I did base my creation off of this. And I kind of designed one using these schematics. But this was one by, I believe, Aswath Raman. He was a physicist that was kind of into this idea. There were a few others, but he was the most popular, I believe. And as you can see, it has it has two sides. It has a radiative cooler and basically like a heat sink on the bottom that's absorbing heat from the ground. The radiative cooler basically absorbs air, basically thermal radiation inside of a space, and then rejects it through a window into the sky. That cools one side, and then the other side basically just absorbs heat from the ground, since it's denser, which means it retains heat longer from the day. The air, of course, loses the heat very quickly, but the ground holds on to it. So then you can take that temperature difference and actually generate electricity. Now, I think this new form of, I believe that if we try to work with this for a while, we might actually come up with a new way to make like a new form of add-on for solar technology that can make living in extreme environments much easier. I mean, imagine it. Imagine by 2060, we're going to have 1 million people living on Mars. So, I mean, if we have a city there, we might as well invest in this technology in order to make living, so much easier. So, yeah, I can't wait to see where this goes. It's only been around for about a year. So, I'm sure it'll definitely come around sometime. And thank you for watching.